Hello, ladies and gentlemen. It's Miss Rector back with you again. Today we're going to talk about the metric system and making observations and measurements. So, first of all, let's talk about the different types of measurements. Qualitative, those are observable things like color, what's its physical state. If you say something is small, that's a qualitative statement. On the other hand, you can make a quantitative statement, which is like an actual measurement. So if you say Ms. Rector is short, that's qualitative. If you say Ms. Rector is 5 foot 3 inches tall, that is a quantitative statement. They're both true. One is just more specific and involves numbers. So when we make these quantitative statements in science, we use the SI unit system. This is based on the metric system. So hopefully you have learned about metric systems somewhere along the way, and this is just a refresher. If not, feel free to pause, rewind, and even look for other resources if you like. So first of all, what is the point of the metric system? Well, let's think just about language. Wouldn't it be nice if every country you went to, everybody spoke the same language? We wouldn't lose things in translation. When people asked each other questions, we would know what they meant. And it would be so easy to just go from one country to another. Me, I'd love to go travel around the world, but I constantly worry that, oh, I don't speak that language. Well, the SI measurement system is how we speak the same language in science. Everybody speaks the same language in math. So, whatever country you're in, 2 plus 2 is 4. Whatever country you're in, it would be nice if we all use the same measurements. So everybody in the world has decided that this is a good idea, and they've all signed on to it, except for a few tiny little countries like Liberia, Myanmar, and of course the United States. Actually, the U.S. did officially adopt it in 1866, but we are stubborn and just don't like to change things here. But we can see where it comes into play and causing some problems. So in the 1999, we made this Mars Climate Orbiter, okay? Supposed to go enter Mars's orbit, and it cost $125 million to build this thing and put it up there. And guess what happened? It was destroyed because somebody used pounds instead of newtons, pounds being the American system for weight, newtons, of course, being metric. So they're not the same thing. So the orbiter didn't know how much fuel to burn, and boom, there you go. This became a cautionary tale. Please stick with the metric system. Everywhere you go in science, people use the metric system. When you go to the doctor, they give you medicines in milligrams, right? They don't give you medicines by the pound or the ounce, it's in milligrams. They give you cc's, so cubic centimeters, standards of measurement. We use a measuring tool. We're going to compare some dimension and measure things. So when we think about a foot, the foot was based on like the king's foot. Well, that's not a standard, right? Every new king has a different size foot. We needed something that would be constant and consistent. So every measurement is going to have a number followed by a unit. You will lose points on work for not putting the unit behind the number. It doesn't make any sense without the unit. If you said to me, Ms. Rector, how far do you live from school? And I said 16, that would not help you. That's not a helpful answer. Does that mean I live 16 houses down? Is it a 16-minute drive? Am I 16 miles away? What does that mean? So you have to put a unit after your measurement. So what are the SI units? We use different units for measuring different things. So we have length, we use a meter. For mass, we use a kilogram. Volume is a liter. Time is seconds. And temperature, well, it's Celsius or Kelvin. And we'll talk more about that when we get into temperature measurement. Now, notice one of these things you're already familiar with. We even use it here in America, right? Everybody uses seconds. Think about time. What if you went to a different country and they used a different measurement for time? You're in Paris and you say, "Oh, I wonder what time the Louvre opens." And somebody says, "Oh, it's 10 harkles past a snap snop." And you said, "I don't know what that means." Well, everybody has to use the same unit of measurement for time because we travel from place to place, and it only makes sense for airplanes and buses and trains to have the same system of time, right? Well, everything else is just the same. Meters, they've all agreed to use the same way to measure meter or length, and that's a meter. And mass in kilograms, volume, liters, and of course, Celsius for most temperatures. Let's talk about mass versus weight. So, mass is the amount of matter. It's measured in grams. You measure it on a balance. So, it's the amount of matter that takes up that space. So, if I were getting my mass, that would be like measuring how many particles were in my body. That's the grams. Now, weight is different. Weight is the force exerted on that mass by the gravity pulling on it. So we tend to measure that here in the US in pounds, right? And we measure it on a scale, not a balance. A scale, it has like a little spring in it, right? So gravity's pushing down on you, makes a spring go down. So if I take that same scale and I suddenly go to the moon, gravity is less there. So it's going to pull down on me less. The spring in the scale is going to go down less, and I'm going to weigh less on the moon than I do here in on Earth. But that doesn't mean I lost any particles. My mass would be the same. So the mass would not change if I were to go to the moon. I'd still have all the pieces that make me up, but the weight would. So again, tools for measuring things. We take our temperature with a thermometer. Volume, we might use a graduated cylinder. Time, stopwatch, of course. And weight, we got a scale right there. So when it comes to questions like this while we're on remote learning, I'll ask the question and then I'll pause for a second for you to think of the answer, maybe longer if it's a math calculation or something, and then I'll give you the answer. So let's and see how you did. But please try to get the answer yourself in that pause. So a bag of tomatoes is 4.6 kilograms. That would be mass. A person is 2.0 meters tall. That would be, see meters, you should think length. Medication contains 0.50 grams of aspirin. When you see the grams, you should think mass. A bottle contains 1.5 liters of water. Liters should be volume. What are some US units that we use? So again, length, you might be used to things like feet and yards. Volume, this gets really weird between volume and weight because we measure fluid ounces and we have weight ounces, and they're two separate things, but they have the same name. Doesn't make any sense. Temperature, we tend to use Fahrenheit, right? So let's talk about the metric prefixes. The metric system is so much easier than our usual US system, and for some reason, we don't embrace it. I don't know why. Kilo just means 1,000. It doesn't matter what base you have. A kilometer means 1,000 meters. A kilogram is 1,000 grams. The prefixes mean 1,000 or whatever number they are. It doesn't matter what the base is. So 1 kilometer is 1,000 meters. Notice how you have the prefix and then the unit. So kilometer. Uppercase and lowercase, it makes a big difference. Capital K is a symbol for Kelvin. A capital M is a symbol for mega. A small m could be meter or milli. We'll see, but we'll talk about that in a second. So centi means 1/100th of a unit, just like a cent, right? There's 100 cents in $1. So 1 meter is 100 centimeters. dollar is 100 cents. Milli means 1/1000th of something. So a milliliter is there are 1,000 milliliters in 1 liter. So here's the breakdown for the metric system. Now, if you think about computers, some of these things might sound familiar. You can have a kilobyte, a megabyte, gigabyte, a terabyte. One day you might have a petabyte computer hard drive, right? On the other hand, when you go down, those are usually for things like medicines and things. You have centi, you can have a centigram, a milligram, a microgram. You may have heard of nanoseconds, right? Nanotechnologies, very, very small, tiny things, right? Then you've got pico, femto, alto. You will do okay in this class if you know kilo through, well, at least milli, but micro, nano might pop up every now and then. You might see a mega here and there. Most people know kilo through milli, and they remember it by thinking of things like King Henry died by, oops, there's a base in the middle there. I'll show you on the steps. King Henry died by drinking chocolate milk. So we'll go on, I'll show you. So when we can write them out as stair steps like this, it will help you convert between them. Notice on these, they all change by 1 decimal place, right? So if you have a meter, okay, if you have 10 meters, it's a decameter. Have 100, that's a hectometer. 1,000 is a kilometer. 1,000,000 is a megameter. So notice how it jumps from 1 decimal place to 3 on these, and all of these are adding 3, adding 3, adding 3 zeros. Same down here. It goes 1 decimal place, 1 decimal place, 1, and then suddenly 3, 3, 3. They're all threes. So if you know kilo through milli, they're all just one stair step away. But once you get into micro, nano, you're going to take 3 steps. So we have kilo, hecto, deca, the base unit. That's whatever your unit is. If it's volume, it's a liter. If it's a time, it's second. If it's length, it's a meter. Then deci, centi, milli. Now, this thing is probably in the way. You got 2 steps here and then micro. So these empty steps, there's no prefix that goes there, but that's because you're no longer moving the decimal place 1 point. You're going to move it 3 to get down to there. And the same with going up here. Mega, if you went up to terabyte, you'd have 3 steps up to tera. So what we're going to do is use this chart to convert. So remember, a base unit, that could be any of the base units, fits right here. So you could say King Henry died by drinking chocolate milk, or you could say kittens hate dogs because dogs can't meow. That's my personal favorite. But remember, it's kittens, not cats. Kittens hate dogs because dogs can't meow. So let's see. Let's go ahead here. If I have 1,000 meters, I have 1 kilometer, right? And then here, remember your math, that's tenths, hundreds, thousandths. I have 1/1000th of a gram, that's a milligram. I have zero 0.1 liters. If you need to go back, you can and say, look at this. Liters a base unit, okay? If I had 10, I'd have a deciliter, but I have 0.1, so I have a deciliter. That's the D for deci and L. By the way, deca is DA, and then deci is just a D. 0.01 meters, so I have 1/100th of a meter. So 1/100th is a centi, so that's a centimeter. So use the staircase and you can go back and forth. Let's say, I'll try and draw in here. I don't do this very well, but let's say I have 2.4 meters. And I want to know, so how many kilometers that is. I'm going to kilometers. All right, so I'm starting off with meters. That's only one thing. There's no prefix. It is a base unit. So I've got 2.4 of these, and I want to go to kilometers. So how many steps is it from the base unit to the kilo? So I'm going to start at base and count. 1, 2, 3 steps. So that means this decimal is going to move over 1, 2, 3 steps. And I moved it to the left because we're going to the left here. Now, my new decimal is going to be right here. I'm going to have to add in some zeros. Bear with me on my drawing here. And so my answer is going to be 0.002. Oh, run out of space. 4 kilometers. So sorry for my messiness there. But you can see when every step you go, you move the decimal. If if I'm going from base to kilo, I'm moving the decimal to the left because I'm starting with tiny little measurements and getting bigger, right? So there's going to be less and less of them. And I'm going this way. If I have a base unit and I'm going to milli, I'm going to go from larger measurements to smaller pieces. So if I have $5, I have 500 cents, right? So there's going to be more of them. All right, let me try and erase this. And then we'll move on. Okay, sorry. All right, oh, go away. There we go. Well, try this again. What the heck? Oh, I can't get that off. Okay, sorry about that. Had to get back out of there. So here we are again. Oh, one more time. Looking at the stair steps. So all you do is move the decimal to the left if you're going this direction, to the right if you're going down. So we're going to try some problems now. Let's try. We've got 500 meters. We want to know how many kilometers that is. So we're starting on the meter step, and we're going to wind up at kilometers. So let's go back to our stair step here. Looking quickly. Say the meter, that's a base unit. I'm going to kilometer. So that's 1, 2, 3 steps to the left. So now where's my decimal in this number? There's no decimal, but it's understood to be here. So you'd go 1, 2, 3 steps to the left, and you'd have 0.5. So you'd have 0.5 kilometers. All right, I'm going to give you a second to try this one on your own. So you have 2.5 meters. You're going to centimeters. Go ahead and try it. Okay. So 2.5 meters, that's where we're starting. And we're going to centimeters. So meters is a base unit. We're going to centi. That's 2 steps to the right this time. So you'd move your decimal 2 steps to the right. So 1 would get you past the 5, and then you'd add another 0. So you'd have 250 centimeters. All right, try this one. One centimeter is how many millimeters? Notice the two lowercase m's. Milli is also a lowercase m. So is meter. We're just running out of m's here in science. So if there's an m in front of it, then it's a milli. It's a prefix. But just an m by itself, that's a meter. So we're at centimeters, going to millimeters. Oops, wrong way. So we're at centi, we're going to milli. That's just one step to the right. So you'd have your decimal here, and it would just be moving it once to the right. So there'd be 10 millimeters. Scientific notation. Gotta love it. So here we are, scientific notation. We've got nanometers here, nanometers. 1 nanometer is this many meters. Now, we've already done the math for you, but this is where we talked about you needing a scientific calculator. Some of these numbers are going to have so many zeros that we have to find a new, shorter way to write them. Coming soon. All right, so why do we have all these things? Let's go back and look at this one more time. The unit for mass is gram. Now, if you're getting like the weight of a person, I don't want to know how many grams I weigh. A gram is about the weight of a paperclip. So it doesn't make sense to say that Miss Rector weighs, I'm going to make a number up here, 149,000 grams. You know, it's just not what you want to hear. I would much rather hear my weight in kilograms, which is a bigger unit. So I can use a smaller number. So if you're measuring your height, what would be the best thing to measure your height in? Millimeters, which are extremely tiny little units. Kilometers, which are long, like there's, a couple of kilometers in a mile. Or meters. Well, meters would be the best thing. That's about the length of a yard. So that would be what we'd measure your height in. What about your mass? I already told you, I don't want to know my mass in grams. So I really don't want to know my mass in milligrams. But kilograms would be a good option. What about the distance between two cities? Take a second. Which one of these would be the best for measuring the distance between two cities? How far is it from Louisville to Lexington? Probably going to go with kilometers there, right? The width of an artery. So again, it's a distance term, but I'm not going to measure that in kilometers. So the width of an artery would be millimeters. Okay, we'll talk temperature. Well, temperature real fast. Why not? So temperature scales, Fahrenheit's what you're used to. Then there's Celsius and Kelvin. Now, we're not going to use Fahrenheit in science class. We're going to use Celsius or Kelvin. Here's the difference. So metric system's always based on tens and zeros. So here's the Celsius. They said, let's take where does water freeze? Let's call that 0. Where does water boil? Let's call that 100. We'll divide that up into 100 degrees and make a temperature scale. Don't ask me how they got Fahrenheit. I have heard lots of different answers and none of them are consistent. Maybe there is some answer out there that's for certain, but I've heard many, so I can't even tell you. But 32, 180, 212, it's just 212. What's water boil at? 212 degrees. It's just a random thing you have to memorize when you could just know 0 and 100. It's easier. So what's up with Kelvin? Well, we can get colder than 0 degrees, right? You can get colder than 0 degrees Celsius. You can get below freezing. We have things that are colder than ice water. So what you wind up having is negative numbers. Now, there's parts of science where we don't want negative temperatures. That messes up our math. So here we have a scale that has no negatives. The 0 on this scale is what we call absolute 0, where all particle motion stops, and you can't get any colder than that. So the 0 is actually 273 degrees below this, but each degree is the same. So a degree Celsius, if the room temperature goes up 1 degree Celsius, it also goes up 1 degree Kelvin. The units are the same. They just start at different places. So it's real easy to convert between these two. Celsius is always 273 degrees lower than Kelvin. Kelvin is always 273 degrees higher than Celsius. So it's pretty easy to go back and forth. Sorry, I should put that up there. 1 degree Kelvin is equal to 1 degree Celsius. They just have different starting points. So if you're ever calculating between the two, you're just going to add or subtract 273. To be real specific, it's 273.15, but we're not going to worry about that today. So body temperature, normally 37 degrees Celsius, would be 310 degrees Kelvin because it's 273 degrees higher. Liquid nitrogen, which is really, really cold at negative 196 degrees Celsius, is only 77 degrees Kelvin. All right, we'll stop there for today. You all have a good day. Practice doing some of these problems. Bye-bye. Where are the office?